quick overview of calculus. Well, this is the magic box of tricks. It's not actually as complicated as people think it is, and it's extremely useful. It was created by Newton and also by Leibniz in Germany at the same time, and they were interested particularly in motion of bodies. So you imagine Newton was looking at planets flying around the sky. He was trying to work out what their tracks were, what their trajectories were, and what the forces were that were operating on them. And he needed a toolkit to do this. So he could no longer rely on just looking at straight lines and gradients. He had to be able to work out things like their gradient on the direction of a curve at a particular point. You might want to know what the tangent to that curve was, or the normal to that curve, and you might want to find the maximum and minimum points of that curve. He was also interested in the area under curves, and that's very useful for us in working out what the energy imparted by a force like gravity is, because you can integrate the work from the force to get that. All of these are functions of calculus, and there's two main arms to it: differentiation and integration. But actually they're basically inverses of each other. So let's have a quick look and work our way through. First thing we might be interested in is might have a curve like this one here. Here's our curve there. This is a quadratic, it's a parabolic curve. And we might be interested in finding a tangent at a particular point. So in this case, let's have a look at a tangent of 5, 4. Well, what do we need to know for that tangent? The first thing we need to know is the gradient. Well, differentiation provides us with the gradient. So if we differentiate this function here, x squared minus 4x, we get the differential. Have a look at a separate video for the detail of it. We get 2x minus 4. So we now know what the gradient is at any point along that curve. And if we want to know, therefore, what the gradient is at the point x equals 5, we just substitute 5 in here. So the gradient of 2x minus 4 when x equals 5 is 2 times 5 is 10, minus 4 is 6. So we now know the gradient of this tangent is going to be 6. And we know from our general formula for a line equation that we know that the next thing we need, the final bit we need, is a point that's going through. And we know that this tangent's going through the point 5, 4. So therefore we can just substitute those values into the general equation, and we get y minus 4 must equal 6, that's the gradient, times 5 minus 6, which you could reorganize into this form. Quite often I quite like that form. So there we are, we've just worked out what the tangent is. Tangent might be the point where a ball rolling around that parabola might be flying off into space. We also use parabolas for satellite dishes, don't we? Because we might be interested in finding the norm there, the normal curve there, the normal line at that point, because if a radio wave comes in here, it'll bounce off that way. Therefore, in similar triangles there, and it's going to come into here, and it's going to hit the so it's going to hit the focus there, and it could, the radio wave could come down this side and hit the focus there, or along that side and hit the focus there. So good uses of it here with the parabola. Okay. Next thing we quite often might want to know is maximum and minimum points for a particular curve. And the important thing here is looking at the gradient, isn't it? Because here, looking at this curve again, at this point the gradient is negative, isn't it? That the curve's going down, and on this side the curve's going up, and there is a point at which the curve is going flat. The line's going flat, therefore at that point the gradient is 0, which means that the differential is 0. Well, we found that earlier, didn't we? For this expression, we found the differential is 2x minus 4. So what we're interested in is that point at which that equals 0. And that equals 0 when x equals 2. And once we know that the x value is 2, then we know the y value is minus 4. So we've just found the minimum point on this curve, haven't we? If we want to convince ourselves that it's a minimum point, we can look at the rate of change of the gradient. We had the gradient was it was negative, wasn't it, here on the left hand side, 0 there and positive there. So what's happening to the change? How's it changing? It's changing in a positive way. How can we prove that mathematically? Well, we can just differentiate the gradient, dm by dx, which is the same as having d2y by dx squared. And if we differentiate 2x minus 4, we just get 2. So here we know that the second differential, the second derivative, is greater than 0. So that means that the gradient's increasing, doesn't it? It started at a negative and it turned into a positive. So therefore we've proved that this is a minimum point, yeah? Because it's gone from a negative to a positive. So that's really useful. So we can use differentiation and setting it to 0 to find all our stationary points, our max and our min. That's really useful. If we were throwing a cricket ball or hitting a cricket ball, we can now find that highest point on it. That's the point, that's going to be our maximum point, and in terms of its height, that's going to be the point where the differential is 0. Okay, what else might we be interested in? We might be interested in the area under the curve. So here's a curve, another quadratic here. So we'll look at that quadratic there. And what we might be interested in is finding this bounded area here. That might be just because we're trying to find the area there. If we were filling it with water or something, or putting foam into that shape, we would need to know the amount of foam to put in. We might therefore calculate that area, and we might extend it to being a volume. So here we go, we want to find the area. So here's our function. Well, we know what our function is, and actually we know that integration is the inverse of differentiation. So if we do inverse differentiation, we can find, integration, we can find the function underneath for the area of this, and then we're interested in finding the difference in that function between what it is at x equals 2 and what it is at x equals 4. So in effect, the first bracket here is we're going to find the difference. So we find the value of the function when x equals 4 here, and then we find the value of the function when x equals 2 there, and then we find the difference between, because we started here and we went to there. Yeah, started at 2 and we went to 4. And if we did that, we find that the area under this curve is 4 2/3. So we talked about using it to find the volume. We could also, if we're working on mechanics like Newton was, we can use it to find the energy that's been imparted to a body, say by gravity. So here we might be looking at bungee jumping, and we might be looking at the amount of energy that's gone into the bungee string that's holding us up as we come down from this top point here all the way down to there. So we've absorbed all that energy there into our bungee string, and then when you shoot up again, all that energy gets released. So that's the sort of thing we can use integration for and areas. So quick summary at the end. Calculus is made up of differentiation and integration. Differentiation's used to find gradients and tangents and normals, and also to find the maximum and minimum points. And we do that by finding the differential here, and the second differential, which would be, so I'm going to write that dm by dx, the rate of change of gradient, and from that we can find what the gradients are of tangents here. So we've done here by finding our gradient. Over here we can find where our minimum point is, because that's the point where it's 0. That's our minimum. And if we wanted to, we can find the area under the curve here by integrating it, which is the reverse of differentiating. So there we are, a quick summary for you of calculus.